If you ask a massive, state-of-the-art 70 billion parameter AI to invent a brand new life-saving drug, it'll almost certainly fail.
Yeah, completely flatlines.
Yeah.
Which is wild.
Right. But if you ask a smaller, supposedly less intelligent AI model to do the exact same thing, it might just find a viable path to curing a disease.
It's totally counterintuitive.
It really is. And today, for you listening, we are looking at the ultimate high-stakes test of artificial intelligence. We aren't talking about, writing a sci-fi script or generating an image of a cat. We are talking about the actual molecular design of medicine.
And that is a fundamentally different landscape. I mean, when we discuss creativity in natural language or art, we're usually talking about aesthetics, like subjectivity.
Does this look good? Does it sound cool?
Exactly. But in drug discovery, creativity is a strict functional requirement. Like a model can't just output a slight variation of a known compound. It has to navigate this highly constrained mathematical space to find something entirely unprecedented.
Which brings us to the core of today's discussion. We're analyzing a preprint paper from April 21st, 2026 by wen-Tao and colleagues. It's called How Creative Are Large Language Models in Generating Molecules?
It's a fascinating paper.
It really is. So our mission for this deep dive is to uncover what creativity actually means when we are talking about chemistry. We're looking at the data to figure out if these massive language models are genuinely original inventors or, if they're just incredibly sophisticated copycats. So, okay, let's unpack this. Because calling a molecule generator creative feels almost, counterintuitive to how we usually think about rigorous science.
It does seem contradictory at first glance. But if you examine how drug discovery operates, the necessity of creativity is just so clear.
How so?
Well, a major hurdle in computational chemistry is getting stuck in what we call local optima.
Local optima?
Yeah, you can think of it like climbing a small hill in the dark. You think you've reached the highest peak, completely unaware there's like Mount Everest just a mile away.
Oh.
Right. If an AI isn't creative, it just takes an existing drug, like aspirin, makes a tiny, obvious structural tweak, and just stops.
So it's not actually inventing anything useful.
Exactly. To find non-obvious solutions, drugs that can pass strict safety tests, be synthesized in a lab, and actually hit novel biological targets, the model has to explore the unknown.
Okay, so to evaluate if an AI is actually doing that, the researchers had to mathematically define what creativity even is in a scientific context.
Which is incredibly hard to do.
Right. And reading through their methodology, the most fitting comparison I could think of for generating molecules is playing jazz music.
Oh, I like that.
Yeah, because you have to follow the underlying chord progression and
Right.
the time signature, right?
Yeah.
And in chemistry, those are the valency rules and physical laws.
Yes. If you break them, you're just making noise. It's not a molecule.
Exactly. But to be a great jazz player, you also have to play notes no one has played before. You have to actually explore.
Right.
So how do the researchers measure those two completely different forces without them just, blurring into a meaningless overall score?
Well, they separate creativity into two distinct measurable dimensions. The first is what they call convergent creativity.
Convergent. Okay, so that's the rule-following part of the jazz framework.
Exactly. It focuses purely on constraint satisfaction, and it's measured by two specific metrics. First is validity. So does the output follow chemical syntax? Like, is it a structurally possible molecule at all?
Okay, that makes sense. And the second?
The second is success rate. Does the molecule actually meet the specific constraint requested in the prompt? So, for instance, if you ask for a molecule that can pass the blood-brain barrier, does the generated structure actually possess those required properties?
Got it. So convergent creativity is just asking, did you follow the prompt without breaking the laws of physics?
That's the baseline, yeah. The second dimension is divergent creativity, which measures the actual exploration.
The jazz solos.
Exactly, the solos. The researchers track three metrics here. First is novelty. Did the AI generate a molecule that is completely absent from their massive reference data set, which is called 𝗬𝗫 250K?
So did it avoid plagiarizing?
Right. Second is uniqueness. When the AI generates a batch of, say, 100 molecules, are they actually different from one another, or did the model just, repeat the exact same successful structure 100 times?
Well, that's smart, because a model could just find one good answer and spam it.
Exactly. And finally, diversity. This looks at the underlying chemical scaffolds. Is the AI exploring entirely different structural families or just swapping out minor functional groups on the exact same base structure?
Okay, the granularity there makes total sense. But if I'm grading this AI, how do I combine a score for following the rules with a score for wild exploration?
That's the tricky part.
Right, because if an AI generates the most diverse, unique, novel molecule in history, but it instantly degrades upon contact with air, it's useless as a drug.
Right. The researchers address that by completely avoiding a simple arithmetic average. Instead, they use a geometric mean to calculate the final creativity score.
A geometric mean? Why is that distinction so critical?
Well, if you use a simple average, a model could score 100% on exploration and a 0% on validity, and it would still walk away with a 50% passing grade.
Oh, I see.
Yeah, but a geometric mean multiplies the values together and then takes the root.
Which means if a model generates entirely invalid molecules, like if its convergent creativity drops to 0, its overall creativity score drops to exactly 0.
Yes, it acts as an absolute fail-safe. It prevents a language model from gaming the system.
So it can't just memorize existing drugs and pass?
Exactly. And it can't pass by generating highly diverse chemical gibberish either. It forces the model to prove it can balance both dimensions simultaneously.
Okay, so now that we understand this incredibly strict measuring stick, we have to look at how the models actually perform. And looking at the correlation matrix in the paper, there is a massive tug-of-war happening inside the brains of these models.
Oh, absolutely. The data reveals a very strong negative correlation between convergent and divergent creativity.
They fight each other.
They really do. Across almost all the models tested, the systems that are exceptional at following rules and hitting constraints are mathematically terrible at exploring the unknown.
And vice versa. Right.
Right. Models that produce wildly diverse, novel molecules almost universally fail at constraint satisfaction. The two objectives actively work against each other.
Let me bring in some of the specific model data here, because this is where the assumptions about AI get completely flipped upside down.
Yeah, this is the best part.
You would assume that if I take a small AI model and I upgrade to a massive one with billions more parameters, I should get like the ultimate creative genius, a model that understands the rules perfectly and uses that deep knowledge to invent new things.
That's the logical assumption, yeah.
But the paper compares models in the llama 3 family, specifically the 8 billion parameter model and the massive 70 billion parameter model, and the heavyweight just plays it incredibly safe.
The 70B models are essentially perfect rule followers. I mean, they hit near 1.0 validity scores. They almost never break chemical grammar.
Right.
But as that parameter count increases, uniqueness and diversity just plummets. They zero in on a very narrow, highly reliable region of chemical space, and they just refuse to leave it.
Right. To put hard numbers on that for you listening, the researchers created a composite metric called the fully creative metric. This tracks the elite subset of molecules, the ones that are successful, novel, ND, unique, all at the same time.
The holy grail of drug design.
Exactly. So the smaller llama 3 8B model reached a fully creative score of 0.556, but the massive 70B model dropped all the way down to 0.205.
That's a huge drop.
Here's where it gets really interesting. The smaller model produced more than double the number of actually useful novel discoveries. So we are actively building multi-million-dollar supercomputers that are mathematically incentivized to be less innovative than their cheaper predecessors. I mean, that is a massive problem for pharma. Why is the big model so rigid?
Well, it comes down to a phenomenon we can call probability mass concentration.
Okay, what does that mean?
When you train a massive 70 billion parameter model on trillions of tokens and subject it to extensive fine-tuning for safety and accuracy, its internal weights become highly confident in the most statistically frequent patterns.
It gets scared to be wrong.
Basically, yeah. It aggressively prunes edge cases to avoid making a mistake. But the 8 billion parameter model is inherently less confident. Its probability landscape is flatter.
So it's a little more ignorant in a good way?
Exactly. That slight ignorance allows it to mathematically wander into novel chemical spaces that the larger model's optimization process has strictly walled off.
It's penalized by its own perfection. That makes sense for the scale of the model. But the researchers also looked at the type of task the AI was given. And they found this massive divide between what they call global properties and specific biological targets.
Right. So global properties are broad physical traits. Things like QED, which is a quantitative estimate of drug likeness. Essentially, does this chemical structure broadly resemble a pharmaceutical?
Okay. And there was another one, right?
Yeah, HIA, which is human intestinal absorption. And the language models are surprisingly adept at hitting these broad global targets, even when evaluated zero-shot.
Meaning they are given no examples in the prompt at all.
Exactly, just doing it from scratch.
But when asked to design molecules for specific biological targets, like binding to the DRD2 receptor, which regulates dopamine, or the JNK3 receptor, the success rate drops to near 0.
They completely fail.
I read this and thought about an analogy. It's like asking someone who has read a million restaurant menus to suddenly cook a Michelin star souffle. I mean, they know the vocabulary, they know it involves eggs, but they completely lack the physical execution skills.
That's a perfect way to put it. And the reason the Michelin star souffle fails is because of how molecules are represented in the AI's training data.
How so?
LLMs process chemistry through text strings, often a format called SMILE strings. They learn the syntactical patterns of these strings across millions of documents, so they understand what a drug-like string looks like.
Right.
But a specific biological target, like the DRD2 receptor, is a physical three-dimensional pocket folded out of proteins.
Right, it's a 3D lock and key.
Exactly. The LLM is trying to design the key based purely on statistical word associations, without ever having the capacity to actually see or simulate the 3D geometry of the lock.
That is wild.
Yeah. When faced with these specific targets, the model's divergent creativity spikes. They generate highly unique, diverse molecules, but it's effectively just random guessing.
Which leads us to one of the most counterintuitive findings in the entire paper. the constraint paradox.
Oh, this was fascinating.
In natural language processing, or, creative writing, adding constraints makes a task harder. If I tell you to write a poem, but you cannot use the letter E, your success rate drops.
Right, it gets much harder.
But in chemistry, the researchers found the exact opposite. When they asked the AI to generate a molecule with high QED drug likeness, it had a baseline success rate. But when they added a second constraint on top of it, demanding a molecule with high QED that must also pass the blood-brain barrier, the success rate for hitting the QED target actually increased.
The mechanism driving that paradox is that chemical properties are deeply correlated. They aren't isolated variables.
Okay, walk me through that.
When you force the AI to satisfy the blood-brain barrier constraint, you are imposing severe limitations on molecular weight and lipid solubility. You are effectively forcing the model onto a highly optimized chemical highway.
Oh, I see. So the secondary constraint acts as a filter for the noise.
Yeah.
By trying to cross the barrier, the molecule is forced into a shape that accidentally makes it a better overall drug candidate.
Exactly. The constraints are cooperative. Adding the specific physical requirement doesn't box the AI in. It actually guides the probability distribution away from chemical wastelands.
Let's expand on how these models handle numerical constraints, because this is where the physical reality of the body really meets the math of the AI. The paper focuses heavily on targeting a property called log P.
Right. Log P is the partition coefficient. It measures hydrophobicity, basically the ratio of how much a molecule dissolves in oil versus how much it dissolves in water.
And for you listening, let's connect this to the physical reality of your body. Your bloodstream is mostly water, but the membrane walls of your cells are made of lipids, which are fats or oils.
Right.
If a drug is entirely water-soluble, it travels through the blood easily but bounces right off the cell wall. If it's entirely oil-soluble, it gets trapped in the fat tissue or clumps in the blood and never reaches the target.
It's a delicate balance.
So a drug designer needs a very specific log P number, say, exactly 2.5 or 3, to perfectly balance that journey. But language models are famously bad at precise math, so how did they handle targeting a specific log P?
Well, they handle it at a population level rather than an individual level.
What does that mean?
If you prompt the model for a log P of 5, it cannot reliably generate a single molecule that hits exactly 5.0 on the first try. However, it understands the directional vector. The entire distribution of the 100 molecules it generates will shift upward toward 5.
Oh, I get it. And if you ask for a log P of -3,
The whole distribution shifts downward.
it's like throwing a dart at a board while wearing a blindfold, but someone tilts the floor toward the bullseye. You aren't aiming any better individually, but gravity, or in this case, the prompt, is skewing your overall mistakes in the right direction.
The environmental shift is a great way to visualize it. You wouldn't trust the model for a single, perfectly calibrated calculation, but you can rely on it to shift a broad chemical library in the right physical direction.
Okay, so since we know the AI fundamentally lacks an understanding of 3D biology, relying purely on its text prediction engine, we have to kind of hack its prompt environment to force it to be creative and accurate.
Right.
How are researchers actually doing that? The paper explores 2 primary methods. The first is in-context learning.
Yeah, so with in-context learning, you place examples directly into the prompt to anchor the model's attention. We noted earlier that for the specific DRD2 receptor, the AI's zero-shot success rate was a dismal 0.150.
Just terrible.
But when the researchers took GPT 3.5 and provided 10 examples of molecules that successfully bind to DRD2, what we call 10-shot learning, the success rate immediately jumped from 0.150 to 0.542.
Over a 50% success rate just by showing it 10 examples. But let me guess, it cheated.
It absolutely cheated. The divergent creativity completely collapsed.
Wow.
Yeah, for the GSK3 beta target, when they provided examples, the uniqueness score plummeted from a near-perfect 0.965 down to 0.406. And the fully creative score barely nudged, moving from 0.150 to just 0.190.
Why does it just start copying the homework?
It's a function of the transformer architecture's attention mechanism. LLMs disproportionately weight the tokens that are immediately present in their context window over the generalized knowledge from their pre-training.
So it gets hyperfixated on the example.
Exactly. When you provide 10 successful chemical scaffolds in the prompt, the model's attention mechanism locks onto them. It successfully hits the target by making trivial modifications to the examples provided, completely abandoning the search for novel structures.
It becomes a highly efficient mimic, but ceases to be an inventor.
Beautifully said.
So if providing examples kills the exploration, we have to look at the second method, which manipulates the mechanics of the model itself, adjusting the inference temperature.
This is where it gets really mathematical.
When the researchers adjusted the model's sampling temperature, cranking it from a conservative 0.25 up to 1.0, we finally see how creativity functions mechanically.
Temperature dictates the shape of the probability distribution for the next token, or in this case, the next chemical bond. At a low temperature of 0.25, the distribution is extremely sharp. The model almost exclusively selects the single most probable, statistically safe bond. It's rigid.
Playing it safe.
But as they scale the temperature to 1.0, the distribution flattens. Lower probability bonds become viable options.
And the data shows this is a sweet spot. At 1.0, diversity and uniqueness steadily climb as the model is mathematically forced to explore wider chemical spaces, but crucially, validity and success rate stay stable.
Yes, that's the balance.
But what happens when they push it to 1.5?
At 1.5, the probability distribution becomes too flat. The model assigns too much weight to statistically unlikely bonds, and the underlying chemical syntax just shatters.
It breaks the rules.
Completely. It starts generating carbons with 5 bonds or impossible ring structures. Validity plummets. Success rate crashes.
The model becomes so mathematically obsessed with injecting randomness that it forgets the fundamental laws of chemistry.
Exactly.
It proves that inference time settings are a delicate balancing act. You can induce exploration, but only up to the breaking point of the syntax.
Right.
So we have covered an incredible amount of ground here. We've talked about geometric means, probability mass concentration in 70B models, constraint highways, and the mathematical flattening of temperature.
It's a lot to process.
It is. So what does this all mean for you? How should the scientific community actually deploy these models today?
The paper provides clear, actionable parameters. First, do not utilize LLMs as autonomous decision makers for designing specific biological inhibitors.
Too much hallucination.
Right. Their lack of 3D spatial awareness makes their zero-shot outputs highly unreliable for complex stocking. Instead, deploy them as broad proposal generators utilizing global constraints.
Because they excel at understanding drug likeness and absorption.
Exactly. You can prompt an LLM to generate a massive, diverse library of drug-like candidates, and then pass that library through traditional physics-based 3D docking simulations to find the actual winners.
And as for which model to choose, it's highly dependent on the task. The data show that for general chemical tasks, balancing both convergent and divergent creativity, GPT 3.5 actually came out as the most capable overall.
Which is surprising to some.
Yeah. But if you are trying to hit those precise numerical constraints, like targeting a specific log p-value for cellular absorption, DeepSeek V3 was the top performer. If you need absolute validity, use a massive 70B model.
And if you need a breakthrough discovery, use a smaller 8B model and push the temperature to 1.0.
It's all about matching the model's specific mathematical biases to your chemical objective, which leads to a final, slightly mind-bending thought that this data brings up.
So let's hear it.
We spent this entire deep dive analyzing how an AI's creativity is not magic. It is a geometric mean of rule following, bounded by constraint highways, and injected with controlled randomness through a temperature distribution. It's highly mechanical, but it makes you wonder. When a human chemist has a massive eureka moment in the lab, or when any human experiences a stroke of genius, are they really experiencing some mystical spark of inspiration?
Oh, wow.
Or is human intuition just a biological version of a high-temperature sampling process? Are our brains just flattening their own probability distributions, randomly exploring the latent space of our memories and experiences until a novel connection finally clicks into place?
It really forces us to ask if we are just biological algorithms running our own internal optimizations for novelty and constraint.
I don't have the answer to that, but it is definitely something to chew on. Thanks for joining us on this deep dive into the molecular mind of AI. We will catch you next time.